Hello all. In our previous lecture, we have seen how K-maps can be used to optimize Boolean expressions, sum of mean terms or product of max terms. We have also seen that in K-maps, if the number of variable increases from 3 to 4, complexity increases. If 4 to 5, the number of variable increases from 4 to 5, then complexity even increases. If number of variables are more, then complexity is beyond control. The best advantage of K-map that it is visually appealing, and we can visually look for implicants and minimize the terms that will be lost as the number of variable increases. Further, there is also, when you solve the problem with K-maps, then you will observe that sometime you will miss a particular optimization or particular combination which could otherwise have been there. So because we rely on our instincts, we rely on our visual capability that whether these two terms can be combined or not. So this visual capability sometimes is limiting, and it does not give us a foolproof method. Other issue is that when you are using K-maps, and let's say you would like to create a computer program, you would like to create a computer program which can help you in optimizing. It would be difficult. It would take a little more time. It would be more number of lines of code which will help you in combining the terms and identifying which one is important and which one is, let's say, prime implicant. So that's why there has to be some other method which can help us in automating, and which can also help us in whatever number of variables are there, it could be effective. So with that purpose, another method has been proposed by a researcher which is quite popular. It's called Quine-McCleskey, or in short it's also called QM method. So in Quine-McCleskey method, the procedure is essentially same. Whatever we were doing in K-maps, we are doing the similar things, but in a tabular method, or in a text-based method rather than a graphical method. So if we summarize what were the steps in K-map, in optimization, Boolean optimization using K-map, the first thing we were doing, we were filling the K-map with all the ones or with all the zeros, and the second one was we were grouping them to form what could be the prime implicants. And then we were trying to find essential prime implicants, means those prime implicants which are very essential because a particular mean term is covered by only one particular prime implicant. Okay, and then finally giving an optimization term. So the same method can be utilized rather than in graphical but in a tabular method. So this method is called QM, or Quine-McCleskey method. So in Quine-McCleskey, the basic principle is still same, that two terms can be minimized or combined if only one variable is different. So let's say xy plus xy dash equal to x. So because y and y dash are present, and if we add both of them, then y can be eliminated. So this x could be only one variable, it could be a set of variables, but essentially they in two terms only one particular variable is different, or one particular variable is present in both complement as well as the original form, then that particular variable could be eliminated. So this is the basic idea. Now in this QM method, again the method is similar. So we have two phases. One phase we find all the prime implicants. So in this phase we are exploring what all implicants are possible. So we enumerate all of them, and in the second phase we cover all the mean terms using these prime implicant. We find that which prime implicant should be included in our final solution. So to find what all prime implicants are there, as a systematic approach, what do? We compare each mean term with the other mean term. So let's say there are n mean terms which are present, so there would be n into n minus 1 comparisons. So we are comparing each mean term with the other mean term and then see whether this minimization is possible or not. So to make it a little easier, so n into n minus 1 become a very large number, so then a grouping is done. Okay, so in this grouping, number of comparison are reduced by grouping. So you see that two mean terms could be combined only if one variable is different. So if two particular mean terms has number of 1 different than more than 1, then it may not be able to group them. So what is done in Quine-McCleskey method, that we arrange all the mean terms in order of number of ones present in those mean terms. So that help us in reducing the number of comparisons. So for example, we compare only with a group of mean terms which has only only one number of ones, and with the other group of mean terms which has two number of ones in them. Okay, so we'll see all these things with example, and then after doing all the comparisons, sometime if some particular pair is redundant, then we can remove here at this stage. So this process would be repeated, like after comparing, we'll get the second stage where where one variable has been eliminated, and then we can have another stage where two variables has been eliminated, and there could be third stage where three variables has been eliminated. So the total number of stages would be equal to maximum number of variables. So that way, till all the variables all the possibilities that all the variables has been eliminated, if that finishes, so we also finish this finding of our prime implicant phase. Once all the prime implicants has been computed, found, and then we start the covering phase. In the covering phase, we see that each mean term should be at least covered by one of the prime implicant. So let's try to understand this whole process with the help of an example. So let's take this example that I have a function f which has two variables a, b, c, d, where a is of most significant and d is the least significant, and the set of mean terms are 0, 1, 2, 5, 6, 7, 8, 9, 10, 14. So as I said, the ideal way would have been that we compare each of the mean term with the other mean term and see if there is a difference of only one variable. So these comparisons would lead here, so the total number of variables here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 into 9, 90 comparisons would be there in first stage itself. So to reduce the number of comparisons, we arrange them. So we arrange in two ways. One, we'll arrange in based on the number of ones. So for example, 0 will have no 1, so it is group 0. And all these mean terms 1, 2 and 8 has total number of ones present in each mean term is 1. So 1, 2 and 8. So similarly 5, 6, 9 and 10, all of these mean terms has total number of 1 in them is 2. Similarly 7 and 14, total number of ones which are present in these mean terms are 3. So we are grouping them in the order of number of ones present in each mean term, and also it is sort of an ascending order. So first would be the minimum number, and after that in each group also we can arrange them in the ascending order. Okay, so let's try to, again I'll try to repeat that what is the logistic here. So see, group 0 can never be combined, can never pair with the group 2, because there are already two ones here and there is only there is no one here. So the condition for combining, condition for pairing is that only one variable should be different, or one variable should be present in complemented as well as the original form. So that means there is no possibility of grouping between known adjacent groups in this method. So group 0 can only combine with group 1, and group 1 can only combine with group 2. or group 0. Group 0 has already been done, so we can discard that. So each group can compare with the other set of the next set of group. So this is how we can combine, and each time we are reducing one particular variable. So let us see it with even like more detail in this particular example. So first in the stage 1 we will write all the mean terms, and also we'll write that this is group 0, group 1, group 2 and group 3. So we are not explicitly writing group 0, 1, 2, 3, it's there in our mind, and these horizontal lines can help us in separating that this is the boundary between group 0 and group 1, and this is the boundary between group 1 and group 2. Group 2 means 2 number of ones, group 3 means 3 number of ones in each mean term. Now to generate the pairs for the second stage, we will compare group 0 with group 1, and the terms which can be optimized, the terms which can be reduced, will replace a dash with them. So for example, 0 and 1 could be combined, so we'll write a pair 0 and 1, and 0 0 0, and because 0 and 1 both are present, so this can be removed and we are replacing it with dash. So similarly 0 and 2 can be combined, and 0 and 8 can also be combined. So with this, because now all the mean terms of group 0 has been compared with all the mean terms of group 1, we are done with the first group of stage 2. For the next group of stage 2, we have to compare all the mean terms which are present in group 1 with all the mean terms which are present in group 2. So 1 would be compared with 5, 6, 9 and 10. So because 1 is compared with 5, we can see that 1 and 5 can be combined, because this particular variable is present as 0 as well as 1, so we can eliminate that and we can write it as 1 5 means 0 dash 0 1. Similarly 1 and but 1 and 6 cannot be combined, because 1 and 6 we see there are 3 variables which are different. However 1 and 9 can be combined. Okay, so we write 1 and 9 here, and the difference in 1 and 9 is only at the topmost bit, otherwise 0 0 1 is same for both of them. So whatever the variable which is different, we are replacing that variable with the dash. Now in the similar way, 2 is compared with 5, 6, 9 and 10, and wherever it find only one variable difference, that a particular pair would be written in this particular group. So similarly, now this whole group would be completed by comparison of this, that means these 3 variables has to be compared with this 4 mean terms. So that means these 3 into 4, 12 comparison would take place, and out of 12 comparison we see that we can have 6 pairs. We got 6 pairs out of these comparisons. Similar to this, so you see here also the total number of ones in this whole group is 1, so we can also call it this group 1. Now similar to creating this group 1, we can go ahead and create group 2 by comparing group 2 with group 3. So group 2 and group 3 of stage 1 can be compared with group 3 of stage 1 to eventually lead to group 2 of stage 2. So you see 5 and 7 can be compared. So if I compare 5 and 7, 0 1 0 1 0 1 1 1. So you see the only this particular variable is present is different here. Otherwise all other variables are same. So 5 and 7 could be grouped, and we can write it as 0 1 dash 1. And similarly 6 and 7 could be combined, 6 and 14 could be combined, and 10 and 12 could be combined. So one more observation here, if we see this observation, then you see that the difference between 2 mean terms so that they can be combined is only 1 or 2 or 4 or 8. So we can recheck from all the pairs. So the difference between 2 mean terms is 1, 2, 8 or 4. Okay, so this is true for all of them. So this gives us another hint that while doing comparison, whether the number of if we do comparison among these groups, so this idea can also be taken that if the difference of the mean term, if the difference of mean term, the lower mean term and the higher mean term, so basically yes, lower means smaller in value and larger in value. So smaller mean term and larger mean term, if the difference is the power of 2, then that means they can be combined. But the condition for this combination is that they should be created in form of these groups, and only the larger number can be subtracted from the smaller number, and then the power should be then the difference should be power of 2. So then they can always be combined. So with this now after this stage 2, we can also keep on doing this process for stage 3 or stage 4. So in stage 3, we again compare whatever are the pair of mean terms or whatever implicants we get in this mean term in this group with the whatever implicants we have in the second group, zeroth group and first group. So now we are comparing 0 1, all the pairs of this group with all the pairs of this group. So if we compare 0 1 with 1 and 5, because here dash appears at different place, so we cannot combine it. So here the condition is dash should appear at the same place and there has to be one variable difference. Now 0 1 and 1 9 can also not be combined because dash is appearing at different place. 0 1 2 6 cannot be combined. 0 1 2 10 also cannot be combined because of same reason, but 0 1 and 8 9 can be combined because first of all dash is appearing at the same place and there is only one variable difference, 0 and 1. So 0 1 8 9 we create a new combination here or new pair here, and the term we'll write it as, because 0 and 1 is here, so we replace this particular variable with dash 0 0 dash. So now 0 1 and 8 10 cannot be combined because dash is appearing at different place. Similarly 0 2 would be compared with all of them. Now if you see 0 2 can be combined only with 8 10. So because dash is appearing at same place and the value then will be 0, this variable is present as 0 and 1, so this most significant one, so we can write it as dash 0 dash 0. So similarly now 0 8 would be compared with all of these variables, all of these groups. 0 8 would be compared with all the pairs present in this group. So now if we see 0 8 is compared, now to make things faster, so we see that wherever dash would appear at same place, so for example 0 8 and 1 9, dash is appearing at same place, so we can combine them. It will become dash 0 0 dash. Similarly 0 8 would be combinationable with 2 10 because dash is appearing at same place, so it will become dash 0 dash 0 dash 0 dash 0. So this is how when all the options would be exhausted, then we will move on to the comparison with the second group. So we will compare all the pairs present in this group with all the pairs present in this group. So from comparison of this pair to this pair, we got these two combinations which are there. So basically 2 6 could be combined with 10 and 12 because you see dash is appearing at same place and there is a difference of this variable, the most significant variable, so it become dash dash 1 0. So similarly 2 10 and 6 12 6 14 can also be combined. Okay, so during this combination we can also see whether the same principle hold or not. So you see that the difference difference between this pair and this pair is again power of 2. So 0 1 and let's say 8 9, the difference is power of 2, that means 8. And similarly if we see the difference between 0 2 and 8 10 is again a power of 2. So first of all, the difference between each pair, it has to be same and it has to be power of 2, so that means they can be combined. So why I am telling that difference part, because if we use this difference part, so that means we can write a systematic algorithm to find out all these implicants at stage 2 or all the implicants at stage 3 or stage 4. So the process could be is algorithmically sound, and you need not to computer need not to write all these tables in the way we are writing. So we can computer can simply create these pairs by looking at whether the difference is more than difference is equal to power of 2 or not. So after stage 3 we again look for is there a possibility of stage 4 or not. So for that we compare all of these implicants, all of these pairs with all of these pairs. So which is, now we don't see any possibility of combination, because dash dash is appearing at this place, and here in none of the implicant dash dash appears at this place. So stage 4 possibility is not there. So that's why we stop it here, and now we'll try to remove the redundant terms. So if we look at the redundant terms, you see this particular set 0 1 8 9 is also equivalent to 0 8 1 9, so we can simply remove this. And similarly we can remove 0 8 2 10, because it is equivalent to 0 2 8 10. Similarly 2 6 10 14 is equivalent to 2 10 6 14. So one of them can be removed. So this way we are we have removed all the redundant terms. Now let us see the list of our prime implicants. To find the list of prime implicants, what we also do is we will go from the higher stage to lower stage, and we see that if all the implicants there are covered by the larger set, then we can simply ignore them. Okay, so to see that, first we'll try to see whether 0 1 has been covered by something there in the stage 3 or not. Yes, 0 1 has been covered here. So similarly 0 2 has been covered by this particular implicant. So this also has been covered. 0 8 has been covered by first implicant of stage 3. 1 5 has been 1 5 has not been covered, so 1 5 will not tick. So then we'll see for 1 9. 1 9 is covered by first implicant of stage 3. 2 6 is covered by the first implicant of group 2 or group 1 of stage 3. Similarly, now we can see 2 and 10 has been also covered. It has been covered here, as well as it has been covered here. 8 and 9 is also covered by the first implicant. 8 and 10 is covered by this implicant. 5 and 7 we don't see here, so it's not covered, so that means this also become a prime implicant. Similarly 6 and 7 is not covered by any of these implicants, they also become prime implicant. 6 and 14 is covered by this implicant, so we can tick this also. And 10 and 12 has been covered by this implicant. 10 and 14 is 10 and 14 has been covered by this implicant, so we can tick this also. Whatever is ticked, so that means that they are not prime implicant, because a larger set exists where these implicants are only subset. So prime implicant are the superset which cannot be combined further. Okay, so because 0 1 0 2 all of these could be combined further, so they are not prime implicant. However 1 5 5 7 and 6 7 are prime implicant, because they could not merge further or grouped further into a larger implicant. So from the stage 2, similarly we have to go to stage 1, and we have to see whether all the mean terms has been covered by at least one of the prime implicant or not, one of the implicant or not. So 0 1 2 8 5 6 9 10 7 14. All of them has been covered, so we can simply tick all of them. So that means these mean terms are not prime implicant, or there is a larger implicant which is present, which can for which these mean terms are a subset of. Okay, so after looking at all these, now we can clearly mark what are our prime implicants. So our prime implicants are 0, 1, 8, 9, 2, 8, 0, 2, 8, 10, and 2, 6, 10, 14, 1 and 5, 5, 7, and 6 and 7. So after finding the prime implicants, we can also see what would be their mean term, what would be the product expression for each of these groups. So let's consider the first variable is D, and the second is C, and then B, and then A. So we can write this particular product term as B dash C dash, and this one could be written as B dash D dash, and this one can be written as C D dash. Okay, this one can be written as A dash, C dash, and D, and this one can be written as A dash, B, and D, and this one can be written as A dash, B, C. So this is how we can find the product term for each of these groups. So with this, our first stage is over. So the summary of this first stage, and if we compare ourselves with the K-map method, so in this method we have exhaustively searched all the implicants, and then we have exhaustively searched for what are our prime implicants. So because the method is systematic, we are comparing each and every term. There is no chance that we are going to miss any implicant. The second thing is because the comparison can be written nicely in terms of an algorithm. So this could also form a nice optimization. So this optimization can be written using a systematic algorithm in any of the high level language like C, C++, Java, etc. So with this finish, like after finishing this prime implicant table, now we find out that which prime implicant should be included in our final solution. To do that, we create a prime implicant chart, implication chart. Prime implication chart means that which prime implicant should be added. Here in all the rows, we write all the prime implicants which are there. We are also writing their corresponding product terms, and then for each column we write all the mean terms. To make things easier, for each mean term which are present in that particular prime implicant, we mark a cross sign. So for example, 0, 1, 8, 9 is a prime implicant, so we can mark a cross sign for mean term 0, 1, 8, and 9. Similarly, 0, 2, 8, and 10, so we can mark corresponding to mean term 0, we can mark cross, and then again for 2, for 8, and for 10. Similarly, we mark the presence of all the mean terms which are present in a particular implicant. Okay, so after creating this prime implicant chart, the purpose of this prime implicant chart is that all the mean terms should be covered by minimum set of our prime implicants. I'll repeat. So what do we want? We want a minimum solution. In a minimum solution, the total number of prime implicants should be minimized. The other condition is all the mean terms should have been covered by at least one prime implicant. So this at least one prime implicant gives us a hint that those mean terms which are covered by only one prime implicant, they are the most important prime implicant, so they become essential prime implicant. So by looking at this table, we see that in which mean term there is only one tick. So 0 is covered by two prime implicants, 1 is covered by two prime implicants. Similarly, 2, 5, 6, 7, 8, 9 is covered by only one implicant, 10 is also covered by two implicants, and 14 is also covered by one implicant. So essentially the implicant which are covered mean terms which are covered by only one implicant, we circle them. So any implicant which is covering only this particular mean term is essential. Essential means we have to take them in our final solution. So because we have to take them in our final solution, so what we can do is we can put a cross here. So like this, we put a cross here for 2, 6, 10, 14, and similarly we put a cross for 0, 1, 8, 9. So putting a cross means that anything which has been covered, so any mean term which has been taken care by this particular prime implicant, we need not to worry about them. So we can put a horizontal line also, that 10 we have taken care of, 8 we have taken care of, 6 we have taken care of, 2 we have taken care of, 1 and 0 also we have taken care of. So what crosses are left? So that means those mean terms we have to find that they also need to be covered. So we see 5 and 7, these are the two mean terms which are left. And what is the best possibility? Just by looking at it, we can say that 5 and 7, this particular implicant is a better possibility, because by including only one implicant, one prime implicant, both these terms could be covered. Okay, so our final solution could be, we can say that these three are the terms which we will say that b dash c dash plus c d dash and a dash b d. So this could be our final solution. Okay, so this is how the covering phase would finish. And the method is generic, it could be applied to all other possibilities. Now sometime whenever we are covering, some special challenges can come. So for example, we don't see any term which creates two essential prime implicant. So let's say for this particular example, my function is ABC, it has only three variables, A is the most significant one, and total number of mean terms are 0, 1, 2, 5, 6 and 7. So I have already created what are the possible implicants, prime implicants, and I have also created this prime implication chart. So in this prime implication chart, these are the terms, these are the prime implicants P1, P2, P3, P4, P5, P6, and if I look at this prime implication chart, I see that all the mean terms are covered by at least two of the prime implicants. So because all the terms are covered by two prime implicants, so we don't know which one is essential, and how do we go forward with. So in such cases, one idea could be that we do a coin toss and we randomly select the first one. So let's say I had to make a choice for the 0th mean term. So for 0 mean term, I have two choices, either I select 0, 1 or basically A dash B dash, or I select A dash C dash. Now let me say that I would like to select the first one, A dash B dash. So because I am selecting A dash B dash, so the process would be that I will take care of 0 as well as this particular implicant will take care of mean term 0 as well as mean term 1. So because both 0 and 1 mean term has been taken care, so I can I can put a horizontal line corresponding to this, and I can put a cross here, so that means 0 and 1 has been taken care of. So that out of the remaining mean terms 2, 5, 6 and 7, just by looking visually I can see that the next possible way would be if I select 2 and 6, so basically B, C dash. So because B, C dash would be able to cover two mean terms, otherwise both of these P2 or P3 would cover only one mean term. So we have the only choice we will have is P4. So we'll take P4, and now correspondingly mean term 2 and mean term 6 can also be removed, and after removing mean term 2 and 6 we are left with mean term 5 and 7, and we see that can be covered by prime implicant 5 or 5, 7 or AC. So the total solution will be So the total solution, sorry, so the total solution would be A dash B dash, B C dash and AC. So this is the way we can solve. So again, for the same particular same problem, let's look at the other solution. Let's say for 0th mean term, instead of selecting P1, if I select P2, what would happen? So let us see. So in this case, I selected P2 for covering my mean term 0. So if I select P2, that means I have to remove these two mean terms 0 and 2 from the table. So if I remove 0 and 2, the remaining mean terms are 1, 5, 6 and 7. So out of that, I see 1 and 5 is the better possibility because it is able to cover two different mean terms. So then I'll select 1 and 5, and after selecting 1 and 5, I can remove mean term 1 and mean term 5 from the chart, and the remaining, out of the remaining mean term 6 and 7, I see I can use P6, that means 6 and 7 AB as in my solution. So in this particular case, I came up with two different solutions. Which are entirely different, but both of them are equivalent because in both the cases total number of prime implicants in my final solution is 3, and in both the cases total number of literals is equal to 6. So they're equal in weight. Both of them are equally optimal solutions. So this is how sometime we have to do with the cyclic dependency, or so sometime this guess based solution or trial and error based solutions, they could lead us to slightly suboptimal solutions. So for that also mathematically we can have some sort of some other elaborate algorithms which can give us optimal solutions. So we are not covering those details in this particular lecture. So this is how we do for this kind of a cyclic dependency cases. Now let us see another case also when our problem or function is not completely specified. So what does that mean? So there are some don't care conditions. So what would we do if there are some don't care conditions? In case of don't care conditions, so you see that in QM method there are two phases. In first phase we try to find all the prime implicants. In the second phase we are covering all the mean terms. So in case of incompletely specified solution, the first phase there is no difference. We treat all the don't care conditions as our regular conditions or regular mean terms, but in the second phase, while creating the covering chart or while creating prime implication chart, we don't list these don't care terms. So because don't care terms are not listed, so they do not contribute to essential prime implicants. So what I'll do is I'll take the same example which we have considered for explaining our QM method, but out of this method, so what I have done is I have taken couple of terms which I created as don't care terms. So let's say the total number of terms otherwise were 10, and out of 10 I created 5, 6, 7 these three mean terms as a don't care terms. So if I do so, because 5, 6, 7 are treated as a regular mean term for first exercise of creating all the implicants, so I can create the prime implication chart in the similar way as the previous example. So these are the list of all of my prime implicants, but these three mean terms 5, 6 and 7, 5, 6 and 7 are not listed in this prime implication chart. Because they are not listed in prime implication chart, so they will not contribute to finding the maximum or the best cover. So the process would still be same, that looking at the chart, we'll first look out that which particular mean term is covered by only one prime implicant. So 0 is covered by 2 prime implicants, 1 is also covered by 2 prime implicants. If we see, then we see 9 and 14, these are the two mean terms which are covered by only one prime implicant. So we can choose those prime implicants as essential prime implicants. So after choosing those implicants as essential prime implicants, now we can remove the mean terms which has been covered by these two prime implicants. So after removing all these implicants, now we see that essentially all the mean terms has been already covered. So this will become the final solution. Final solution would be these two essential prime implicants and the product term corresponding to these prime implicant, that means B dash C dash plus C D dash. So this is the final solution. So with this we finished with this QM method of logic minimization, and we can summarize that this QM method is more systematic because it is exhaustive in nature. You don't miss out any particular prime implicant, and it is also systematic in finding essential prime implicants and doing the optimizations around that. So this is with respect to K-map, we can see that it is more systematic approach. The better part or another bigger advantage of this QM method is that we can write algorithms for it. So we can write C++ code, or we can write in terms of a high level language, so that we can minimize whatever given number of mean terms are there. So another summary so far, whatever we have seen, whatever in from the previous 2-3 lectures. So another summary is that the underlying method for minimization is essentially same. We were using same methods when we were similar combination theorems were used when we were using Boolean algebra, and similar methods or similar theorems were used when we were doing combination or finding implicant or minimization using K-maps. Similar methods are used here. So this knowledge, this understanding how two mean terms or how two variables get combined, or can how one particular variable get optimized out of two product terms. So this particular method, this particular understanding can be used interchangeably also. So whenever you are looking at two algebraic terms, then also you can keep your K-maps in your mind, and then can help you this can help you in doing optimization. Similarly, when you are doing KM or K-map based method, then also those algebra, that algebra should be there in your mind, so that you can do optimization in a better way. You can cross check your optimizations, and yeah. So this is how we can do two-level minimization. So we call it two-level minimization because the end result is always either sum of product or product of sum. So there would be two level of logic, AND gate and then OR gate, AND gate followed by OR gate, or a NAND gate followed by NAND gate. So because the total number of gates in all these solutions would be 2, so it's called two-level minimization. So with this, I'll close today's lecture. Thank you very much.